Good morning, Manoj. Morning, Nancy. You can start recording. So we'll start with the morning quote. Remember, a person can succeed at almost anything for which they have unlimited enthusiasm. Okay, that is more important. So many times I say, whatever we do, we have to have the passion. Usually we do anything because of two reasons. One is either fear or the second one is passion. One of these two definitely will be there. Whether you study or you go somewhere or you do something, whatever you do. So these are the main two reasons. One is fear. Fear means there is no other way, you have to do it. So because of some force, some pressure or something, you have to do it. So that is fear. The other one is passion. So because you are interested in it, right, you do it. So when you do something of your passion, you will have real joy out of it. And you will not get tired also. If you have passion, whatever work you do for that, throughout the day you sit, you don't get tired. And naturally you will have so much enthusiasm. And when you do something with enthusiasm and passion, naturally success follows you. Okay, today's quote is given by Mark Twain, the great writer, who is the writer of Tom Sawyer, Huckleberry Finn, and other things. So many beautiful books he has written, not only for elders but also children. Okay, he says continuous improvement is better than delayed perfection. So many times that's what we do. We want to do something perfect, and we will wait for that time. Okay, so you go on postponing it because I want to do it better. So sometimes that time may not come at all. So it is always better for continuous improvement instead of sudden perfection. And actually, this is yesterday's. Yesterday is the birthday of some great ornithologist. He is Salim Ali. Okay, today is the birthday of the great singer P. Sushila. I think there will not be anybody not knowing her in South India. And so S.P. Balasubramaniam and P. Sushila, they have thousands and thousands of songs. She has been recognized by the Guinness Book of World Records for performing a record number of songs in different Indian languages for over 6 decades. 6 decades. She is well known for her mellifluous vocal performances for over 50,000 film songs across South Indian languages. She is fondly called Gana Kokila and Gana Saraswati. She is also considered as one of the rich voiced singers whose pronunciation of the syllables are to be very clear and precise in any of the languages she sang. And anyhow, North India, the way the Lataji is so famous, so in the same way, Sushila ji in South India. Okay, before starting, I want to say Happy Diwali. I may forget about it. So because tomorrow is the Diwali, may your life also be filled with colors and lights of happiness. Happy Diwali to all of you. And today is the lecture 35. And here, just we'll recollect what we have done in the previous class, and then we do problems only. And so last class, we have done the nature of spontaneous processes. We have seen that whenever there is a gradient, whenever a system is at different conditions than environment, spontaneously tries to reach the or approach the environment conditions. So that is spontaneous. And so if there is higher pressure, it will always try to expand and reach the environmental condition. So the dP by dV is always less than 0. In the same way, if the temperature is high, so again the temperature tries to come down and entropy increase, and dT by ds is less than 0. So negative slope will be there on PV diagram and TS diagram for spontaneous processes. And exergy of heat. So if whenever you have heat, because all of that cannot be converted to work, and there will be unavailable energy. So we have seen that W max, that is the available energy. W max is equal to 1 minus T naught by T into Q. Q is the heat and T naught is the environmental temperature. So you can find out what is the maximum available energy out of the given heat, and the remaining is unavailable energy. And also we have seen that out of this available energy, only some of it can be useful work because of irreversibilities. And we have defined irreversibility as W reversible minus W useful. And from that, we have defined the second law efficiency also as W useful by W reversible. Okay, for heat pump and refrigerator, corresponding definitions we have seen. And exergy work. So though we have this much of work, and some of it is spent on the surroundings, right, during expansion. So that is unavailable energy, and that part of work which is available energy is the exergy out of the work. And exergy of mass, okay, mass always constitutes some exergy. So if it is a flowing one, it is psi. Psi is the flow exergy. So when it is entering and leaving, so m dot into psi1 minus psi2 is the exergy increase in the system. And then we have seen what is exergy of closed system. All of them are to be considered. And we have developed the relation, exergy of a closed system, which we defined per unit mass as phi. Similarly, for flow system, if you add flow work to that, we will get the exergy of the flow system. For unit mass, we have defined it as psi. And then we have developed the balance relations. We have done the mass balance, energy balance, entropy balance, exergy balance, and all of them we have done. And then we'll see how it can be used. And reversible work, so when we have defined exergy destruction also. Irreversibility is nothing but exergy destruction, because this much of available energy is there, and while making it useful, I am losing something. So that is destroyed. So that is exergy destruction, and also it is irreversible. And also sometimes we call it as a lost work, because the and also from the energy balance index, entropy balance and exergy balance, we developed the relation for exergy destruction. Exergy destruction is equal to T naught D S gen. Okay, so T naught S gen, T naught into entropy generated is exergy destroyed. So we can, one thing you have to remember is always, this is the general thing you have to remember, always for any natural process, there can be increase or decrease of entropy of the system, but entropy is always generated. Okay, so entropy generation is always positive. Entropy change can be positive or negative based on the heat is taken or taken out or something. In the same way, exergy also, whenever a process takes place in the system, exergy can increase or decrease. There is no problem, right? But exergy always is destroyed. So exergy destruction is positive. Entropy generation is positive. Exergy destruction is positive. Change of entropy and exergy can be positive and negative for a system. Okay, so these are the things you have to remember. So these are the things which we have done in the last class. Exergy of potential energy and kinetic energy, complete energy is available. Okay, whatever is the potential energy and kinetic energy available, it is available energy. Nothing is unavailable out of potential energy and kinetic energy. Okay, these are the normal four things, right? So when you have potential energy, kinetic energy completely available, and when Q is there, only this much is available. If W is there, only this much is useful. And so whenever there is a decrease in the temperature source, there will be decrease in the available energy. There will be decrease in the available energy, and the unavailable energy increase. And okay, this is the exergy of closed system. And here we can see that phi is equal to U minus U naught plus P naught into V minus V naught minus T naught into S minus S naught plus C square by 2 plus GZ. Okay, this is the whole availability of a closed system. When you come to the open system, we add the flow work here, and instead of internal energy change here enthalpy will be there. So psi is h minus h naught, t naught into s minus s naught, plus c square by 2 plus gz. So that is the exergy of the system depends on not only its own properties, but also environmental condition. So I have to find out, if I want to find out the exergy of a closed system or open system, the properties are H, S, C, and Z are the properties of the system, and H naught, T naught, S naught, these are properties of the environment. And using this only, I can find out how much I can extract, or how much is the available energy of the particular system. So, and it is a state property only, right? So that is the way I have to find out. And this is exergy at a particular state. So if the state is changed from 1 to 2, then the change in exergy is psi2 minus psi1. So then h1 minus h0 minus h2 minus h0, like that I will get. And so change in exergy for closed system is u2 minus c1 plus p0 into v2 minus v1 minus t0 into s2 minus s1 plus half c2 square minus c1 square plus g into z2 minus z1. This is change in exergy of a closed system going from state 1 to state 2. And similarly, for a flow system, we get this psi2 minus psi1. And so this is exergy destruction. Exergy destruction is equal to T naught into entropy generated. Okay. So x1 minus x2 is the irreversibility or exergy destruction. I have initially this much of exergy. During a process, it is reduced to x2. So this, whatever is lost, okay, this is lost work or irreversibility or exergy destruction. So x destroyed is always greater than or equal to 0. If it is greater than 0, it is real process. If it is less than 0, impossible process. Equal to 0, ideal or reversible process. So this is also called as principle of decrease of exergy. Like the principle of increase of entropy, we have principle of decrease of exergy, where change of exergy is less than or equal to 0. So change of entropy greater than or equal to 0. ds is greater than or equal to 0. Here dx is less than or equal to 0. This is the principle of decrease of exergy. So for every real process, entropy of the universe increase, exergy of the universe decrease. As I told, that is the death of the universe. So the exergy gradually decrease, and finally it becomes 0. No available energy. When the complete temperature of the whole universe is T naught, so nothing can be done. Everything is dead. Okay, dead state. That is the death of the universe. Okay, here we have done the mass balance and energy balance for the generalized process. Then we have seen what happens to steady state. Then for single stream, for unit mass, and then closed system. And for closed system unit mass, we have done all the things, both for everything: mass balance, energy balance, and entropy balance, and exergy balance. Okay, these are the main basic equations of thermodynamics that you have to know. So reversible work, as I told, when x destroyed is 0, W is equal to W reversible. So W reversible is m into psi1 minus psi2 plus 1 minus T naught by Tk q dot k. Okay, if there is no heat transfer, change in exergy only is the reversible work. Okay, this is the maximum work we can extract. Initial exergy is this much, final exergy is this much. So the difference in the exergy is the maximum available energy, and that is W reversible. Okay, so W reversible is x1 minus x2. Okay, we will see some of the problems. Actually, these are taken from Cengel only. So first we will see the problems that are discussed in the Cengel. Later we can go for the other problems, exercise problems and math problems, because there is plenty of time available. Okay, this is a wind turbine with a 12-meter diameter is to be installed at a location where the wind is blowing steadily at an average velocity of 10 meters per second. Density of air is given 1.18 kg per meter cube. determine the maximum power that can be generated by the wind turbine. Okay, so you can see it because velocity is given mainly the kinetic energy, right? So the kinetic energy is the one that is available in the blowing wind. So how much kinetic energy is the available energy that we have already discussed? That is complete kinetic energy is the available energy. So you have to determine the maximum power means just I have to find out the available energy, which is the kinetic energy. We know that kinetic energy is half mv square. So kinetic energy, available energy is equal to the kinetic energy, that is half mc square. Okay, so C is given from 10 meters per second, and M is rho AC. M dot is equal to rho A C. Rho is given, I think 1.18 is given, and A, for A, the diameter of the windmill is given, 12-meter diameter. So pi d square by 4 you can put, and C is given. So that's all are needed. So rho is equal to 1.18 and pi and d square by 4 into 10. This is the mass flow. Okay, and so if I want x of m dot is 1. Into c square is 10 square. Okay, so this is because mass flow rate is multiplied, so this is kilowatts. Okay, this is the way we have to go about it. And another problem, consider a large furnace that can transfer heat at a temperature of 3000 Kelvin at a steady rate of 3000 kilowatts. Determine the rate of exergy flow associated with this heat transfer. Assume the environment temperature is 300 Kelvin. Okay, so Q is given. So what is the available energy out of Q that is available? So we have the formula 1 minus T naught by T into Q. So T naught is given, T is given. Okay, just it's a straightforward one. So X for Q, right, is W or right X itself. So X is equal to 1 minus T naught by T into Q. So that is equal to 1 minus, I think it is 300 by 3000 into Q is again 3000 kilowatts. Okay, so this many kilowatts. So it is, you can see 300 by 3000 is 0.1, 1 minus 0.1 is 0.9 into 3000. So that is 2700 kilowatts. So this is also reversible work. And you can find out what is unavailable energy. So unavailable energy is Q minus W reverse. So I have 3000 available, 3000 heat that is supplied, out of which this is the available energy. W reversible is X, also available energy is equal to W reversible. All are same. W max, W reversible, available energy, exergy, right? All are same. And unavailable energy is Q minus available energy. So that is 3000 minus 2700. So that is 300 kilowatts. So it is the unavailable energy. So we'll see another problem. A heat engine receives heat from a source of 1200 Kelvin at a rate of 500 kilowatts and rejects the waste heat to a medium at 300 Kelvin. The power output of the heat engine is 180 kilowatts. Determine the reversible power and irreversibility rate of this process. Okay, determining the reversible power as we have done previously, right? Previous problem. And the power output of the heat engine, that is useful work, is given as 180. So difference between reversible work and useful work is the irreversibility that I have to find out. So 1200, 300, 500. So W reversible is equal to 1 minus T naught by T into Q. So 1 minus 300 by 1200 into, I think, 500. 500. So this is 1 minus 300 by 1200 is 0.25 into 500. So that is efficiency of the engine is 0.75 or 75% into 500. So this is equal to 375. Okay. So 375 kilowatts. 375 kilowatts is the available energy. Available energy is equal to 375, which is also W reversible or X or W max. So unavailable energy is 500 minus 375, that is 125 kilowatts. Now W useful is given as 180 kilowatts. So you can find out irreversibility is equal to W reversible minus W useful, that is 375 minus 180, so 195 kilowatts. This is the irreversibility. And you can find out even second law efficiency. Second law efficiency is first law efficiency by Carnot efficiency. Is it possible here? Yeah. And the first law efficiency is W useful by heat supplied. So 180 by 500, how much it is? I think 36%, 0.36. So this is equal to 0.36 divided by Carnot efficiency is 0.75. So divided by 0.75 is 48%. So you can see that the first law efficiency, if I just calculate, because out of 500 kilowatts, I am getting a work of 180 kilowatts, it is only 36%. But we should not be disappointed so much because the maximum efficiency itself is 75%. So compared to that, I have 48% efficiency. Okay, that is the way the use of second law efficiency. Is it okay, everything what I am going?
Okay, sir.
Okay. Right. So that's what it is done here. Okay, reversible work, it is 375 kilowatts, and the irreversibility 375 minus 180, 195 kilowatts. Okay, 500 kg iron block shown is initially at 200 degrees centigrade and is allowed to cool to 27 degrees centigrade by transferring heat to the surrounding air at 27 degrees centigrade. Okay, it's so determine the reversible work and the irreversibility for this process. Okay, and so I have a iron block at 200 degrees centigrade. It's just put in the surroundings, which is at 27 degrees centigrade. So gradually, as time proceeds, it goes to 27 degrees centigrade. All the heat is lost actually. And the only thing is, if I want to find out what is the reversible work, actually there is nothing work, no work. Useful work is 0 because I am not doing any work. Reversible work means what is the maximum energy I could have extracted, right, if I use that particular energy. But only thing is here, which is high temperature reservoir, 200 degrees centigrade, it is not at a constant temperature. It is not a constant temperature reservoir. So it is gradually its temperature is decreasing. Okay, so I cannot just do 1 minus T naught by T. Okay, T is not constant. So I have to integrate it. So how to do that? What happened to my board? So that is actually the W reversible or exergy is equal to 1 minus T naught by T. Here, because I have to integrate, I will write as delta X or delta W reversible into delta Q. And I have to integrate this from T to T naught because temperature is changing from T to T naught. And so this delta Q is nothing but MCP dt, okay, MC dt. So if I substitute that integral T to T naught, 1 minus T naught by T MC dt, I can integrate it. So I think T naught is 27 degrees centigrade given, I think that is 300 Kelvin, and the other temperature 200, that is 473. This is 473. Okay. So if you integrate this, MC will be constant, and integral 1 is T, so T minus T naught by T, 1 by T, dt by T means log T, T2, or 473 to 300. So that is M is given, C is given, I think C will be given. It is not typed here, but C will be known. So M will be given, C will be given. Here I have to write it as U naught minus T minus T naught log T. Okay, so this gives you what is the reversible work. And the irreversibility, because everything is lost, right? So irreversibility is W reversible minus W useful. So W useful is 0. So because nothing is extracted, so I is equal to W reversible. The complete maximum work, whatever is possible, everything is lost to the surroundings. It is irreversible. Okay, that's. So this is the way it is. So MCV, okay, this is minus MCDT, only one negative sign will be there. So here, because heat is lost, so this is MCD minus MCDT. So this will be T minus T naught. This is minus and this is plus. Okay, so this is C, specific heat is given as 0.45 kilojoule per kg Kelvin. That is iron block. So for that you can get from the data books. And 500 is mass, and this is 473 minus 300 into log 473 by 300. Okay, this is the way we can find out the reversible work. Okay, this I think last class we have discussed about it. Second law efficiency is first law efficiency by the reversible Carnot efficiency, and so which is W useful by W reversible. And for refrigerator and heat pump, W reversible by W useful it will be, right? Because I have to give more work. Input whatever I have spent, that is more than. So this is the minimum work that is to be given to run the refrigerator or a heat pump by W useful. So if you divide this, if you write this as QL by or QH by like that, then you'll get COP by COP of refrigerator. We know that COP of the reversible one is the maximum one. COP of the actual one will be less. So COP by COP reversible give the second law efficiency. So you can see here also, and if thermal efficiency is 30% and reversible one is 50%, then you can find out what is the second law efficiency. So like this, thermal efficiency is 30%, reversible efficiency is 50%. So 30 by 50 is 60%, that is the second law efficiency. And if thermal efficiency is equal to the reversible cycle efficiency, so this is reversible. That's why the efficiency, second law efficiency will be 100%. Okay, the iron block discussed in the previous example is to be used to maintain the house at 27 degrees centigrade, and the outdoor temperature is 5 degrees centigrade. Determine the maximum amount of heat that can be supplied to the house as the iron cools to 27 degrees centigrade. Okay, here, what we do is so the outdoor temperature is 5 degrees centigrade and house temperature is 27 degrees centigrade, and determine the maximum amount of heat that can be supplied to the house as the iron cools to 27 degrees centigrade.
T0 is 5 degrees, but limit should be 300 to.
Okay, here let's write CO2. If I have actually the previous one, we get what is the W reversible. Okay, we get 8191 kilojoules. Okay, in the previous problem, so 8191 is the kilojoules. But if you find out MCDT, that is Q, if you find out, it will come to 38,925. So this is the Q, and if you run a heat engine, you may get 8191, out of which you will have, that is because of which unavailable energy will be 30,734. Okay, so if I have a heat engine which produces 8191, and if I can run a heat pump between this 27 degrees centigrade and 5 degrees centigrade, and if I have a heat pump which takes that 8191 W, okay, if I am heating this house is 27, okay. I think this is the house. This I am heating from the environment. This is environment. This is house. So here, if I use the TH by TH minus TL, means 300 by 27 minus 5, 22. So this is actually 13.6 is the COP of the heat pump. So if COP of the heat pump is that, and if W is 8191, I can find out what is Q. COP into W. So that is 13.6 into 8191, and I can supply 111 398 kilojoules. Okay, this much of heat that can be supplied to the house to heat it. Okay, that's it. So determine the maximum amount of heat that can be supplied to the house as the iron cools to 27 degrees centigrade. Okay, so that's it. A dealer advertises that he has just received a shipment of electric resistance heaters for residential buildings that have an efficiency of 100%. Okay, what do we mean by efficiency is 100%? So whatever electric power I am spending, that much of heat I will get out of it. Okay, so actually here we call the COP of this electrical heaters is 1. Means the heat supplied is equal to the work that is given. Okay, and assuming an outdoor temperature of 21 degrees centigrade and indoor temperature of 21 degrees centigrade and outdoor temperature of 10 degrees centigrade, determine the second law efficiency of these heaters. So first law efficiency is 100%, that is 1. And so what is second law efficiency? So I have to find out what is the COP of reversible one. Okay, the 21 degrees and 10 degrees. 21 degrees COP reversible is equal to pH by pH minus. So 21 degrees means 273 plus 21. By 21 minus 10, 11 degrees. So 294 by 11. So that is COP of reversible one. And COP of the heater is 1. So second law efficiency is equal to COP by COP of heat pump. Okay. That is reversible. COP reversible. So this is the 294 by 11.
So efficiency is 1.
Okay, whatever we want, actually heat out of it. We are giving work and getting heat. Am I right? Am I right? Electric heaters, I am giving electrical work and I am getting heat out of it.
Yes, sir.
So COP of the electric heaters is 1. Whatever work I am giving, that much of heat I am getting. This is first law COP. Okay, based on the first law, COP of the heaters is 1. And COP of reversible one is 294 by 11, which is 26.73. So this will be 1 by 26.73. So I should have 26.73 COP, but it has only 1. Okay. So if you take inverse of it,
0.0374.
yeah, 0.37. Right. That's it. So that is so much of thing is waste, right? That's why many times I told in direct heating is very, very inefficient, right? But anyhow, if you want to heat the room, we'll directly heat it. But if you have big buildings and all, we have to use the heat pumps. Okay, this is this. Okay, and COP, yeah, Q dot E equal WE. The COP of this is 1, and the COP of HP reversible is 26.7. So 1 by 26.7 is 3.7% or 0.037. A 200 meter cube rigid tank contains compressed air at 1 megapascal and 300 Kelvin. Determine how much work can be obtained from this if the environment conditions are 100 kilopascals and 300 Kelvin. That is, I have to find out the exergy of the compressed air. Okay, exergy, it is a rigid tank. It is a closed system. So for a closed system, I have the pressure and temperature given, and P0 and T0 also are given. So you can find out what is the phi of the system. So that is the way. And so here, this is the way we do. Exergy is U1 minus U0 plus P0 into V1 minus V0 minus T0 into S1 minus S0 plus V1 square by 2 plus GZ1. This is the total exergy of a closed system formula. And here, there is no change in temperature, 300 here and 300 here. That's why U1 minus U0, it is 0. And no velocity or potential energy. This is only this thing will be there. P0 into V1 minus V0 minus T0 into S1 minus S0. So this V1 is given by RT1 by P1 and V0 is RT0 by P0. So you can write this as RT0 into P0 by P1 minus 1. And to find out S1 minus S0, it is not S2, it is S1 minus S0. T0 into Cp log T1 by T0 minus R log T1 by P0. And because temperature is same, T1 by T0, this goes off, minus R log T1 by P0, we have to put RT0 log T1 by T0. So add this minus this. So writing that here, RT0 into log P1 by P0 plus P0 by P1 minus 1. So it is the function of only P1, P0 and T0. Okay. So we know here these values and you have to substitute. That is the exergy or the available energy of the compressed air that is in a tank. Okay. So this is the way we have to find it. Okay, it is done here. Okay, here this is per unit mass flow. If I want to have the complete exergy, X1 is M151, and because the tank volume also is given. So whenever pressure, volume, and temperature all are given, volume, not specific volume, the total volume is given, immediately you have to find out the mass, because anything, entropy or energy or exergy, whatever you find out, if mass is known, you have to find out full exergy or full entropy, okay, not per unit mass. Okay, so here P1, V1, T1 are given in the problem, 200 meter cube is given. So I have to find out what is the mass. And then you have to multiply that this by mass. So P1V by RT1 is equal to 23 kg. And phi is RT0 into P0. This formula, we just substitute and get it. So the total exergy is M151 to 81 megajoules. Okay, that is the way we have to find. Okay, refrigerant 134A is to be compressed from 0.14 megapascal and 10 degrees centigrade to 0.8 megapascal and 50 degrees centigrade. Okay, state 1 and state 2 are given steadily by a compressor. So it is compressed from state 1 to state 2. You can see initially it is 0.14 megapascal, but now 0.8 megapascal. Its pressure is raised, and due to compression, temperature also increased. And taking the environment conditions to be 20 degrees centigrade and 95 kilopascals, determine the exergy change of the refrigerant during this process. Exergy change means because it is a flow system, you can take Psi2 minus Psi1, and Psi2 minus Psi1 is H2 minus H1 minus T0 into S2 minus S1. Okay, so H1, H2, S1, S2 I have to find out. T0 is given. Okay, so you can find out what is the change in exergy. So how to find out H1, S1, H2, S2? You have to use the refrigerant 134A tables. So you have superheated tables for 0.14 megapascal and 10 degrees centigrade. You can find out what is H1 and S1, and 0.8 megapascal and 550 degrees centigrade also. You can find out what is H2 and S2. Okay, so we will see whether it is done that way. Okay, formula is this: H2 minus H1 minus T0 into S2 minus S1, and so Psi2 minus Psi1, it is found out to be 38. I don't know whether the values are there. So at P1 and T1, 0.14 megapascal and minus 10 degrees centigrade, from the tables, here you get H1S1, and exit state again from this at T2, T2, you get H2 and S2. Just substitute them, we get. Okay, so this is the way we have to go about. And okay, this also we can give some idea why entropy generated and exergy destroyed. If I have a wall here with two temperatures, T1 here, T2 this side, so some Q is transferred, heat is transferred from here to the here. So what is the entropy that is transferred here? Because T1 is there, Q is known, Q by T1, and here the entropy is Q by T2 because this side T2 is there. So because T1 is high, that Q by T1 is small, and T2 is small, and Q by T2 is high. So the entropy that is entering is only Q by T1, which is small, and it is leaving with Q by T2, which is large. And so you can see that this difference, right, is the entropy generated. Okay, there will be one or two problems also in the exercise and other thing. And if there is Q going like this and the temperatures are T1, T2 on the other side, what is the entropy generation? Okay, so Q by T2 minus Q by T1, that is the entropy generated. In the same way, exergy for a given heat Q, the exergy is 1 minus T0 by T1 Q. T0 is the environment temperature. Okay, so that is same on both sides. So 1 minus T0 by T1 into Q is the exergy initially before entering, and after coming it is 1 minus T0 by T2 Q. So you know that this is less and this is more, okay, because I am subtracting small amount from 1, and here subtracting large amount from 1. Okay, so here the initial exergy is this much and final exergy is this, and we are losing exergy. So exergy destruction is 1 minus T0 by T1 into Q minus 1 minus T0 by T2 into Q is the exergy that is destroyed. Okay, so that is the way we can find out, and just it logically gives you so why entropy generates and exergy destroys, because when you calculate the T1, T2, which are of different values, so the magnitudes of T1 and T2 decides the entropies and exergies. Okay, is it clear? So this is what indicates. So whenever there is a process takes place, destruction of exergy is always positive, and change of exergy of a system can be positive, can be negative. The exergy change of a system can be negative, but the exergy destruction cannot. Okay, consider steady state heat transfer through 5 meter by 6 meter brick wall of a house of thickness 30 centimeters. Okay. So on a day when temperature of outdoors is 0 degrees centigrade and the house is maintained at 27 degrees centigrade, the temperatures of the inner and outer surface of the brick wall are measured to be 20 degrees centigrade and 5 degrees centigrade respectively. And the rate of heat transfer through the wall is 1035 watts. Determine the rate of exergy destruction in the wall and the rate of total exergy destruction and at the wall exit it is 5 and outdoor it is 0. Okay, it is something like that. Okay, this is a room, this is outdoors, and here this is 27 degrees centigrade and here it is 0 degrees centigrade, but near the wall it is 20 degrees centigrade, 20 only, this is 5 degrees centigrade, 20 and 5, and heat transfer is 1035. And 35 watts. Okay. So here, if I want to find out what is the exergy destroyed within the wall, I have to use this temperature and this temperature, use the previous formula. And if I want to find out the whole one, okay, so what is asked? The total exergy destruction associated with this heat transfer process, the whole heat transfer process. So I have to find out with the 27 and 0. So we'll see how it is. So here this is the way, and this is 27, this is 20, this is 5, this is 0, this is 30 centimeters, and Q dot is given. So here for the wall only, if I consider Q dot into 1 minus T naught by T in minus Q naught into Q dot into 1 minus T naught by T out minus X destroyed is equal to 0. And so this is 1035, and this is 273, and here this 20 is taken here, 293. And here 5 degrees is taken, 278. Okay, so this is the way I have to find out. So this is exergy destroyed within the wall, and so the total exergy destroyed is 1035 is same, but here 273 by 300, that is 27 degrees centigrade I have to take, that is 300, and this side 1035 into 1 minus 273 by 273, actually this will not be there at all. Okay, this is 0. So this is the total exergy destroyed. You can see that within the wall, the exergy destroyed is only 52. And if you consider the outside also, because it is coming from there to here and then it is going, it is 93.2 watts. This is the total exergy destroyed. Okay, another problem. A piston cylinder device contains 0.05 kgs of steam at 1 megapascal and 300 degrees centigrade. So again, the steam conditions are given at the beginning. So 1 megapascal and 300 degrees centigrade. So if I want to find out its properties, I have to go to steam tables. And mass flow is given 0.05 kgs. So never forget about the mass flow. Okay. And steam now expands to a final state of 200 kPa and 150 degrees centigrade doing work. So at the exit conditions also, the pressure and temperature are given, means both are superheated state only. So it is expanding. And heat losses from the system to the surroundings are estimated to be 2 kilojoules. So when you do the exergy calculation, this Q also will be useful because you have to find out how much exergy is lost because of it. Assuming surrounding temperature T naught, P naught. So you have to find out exergy of the steam at the initial and final states. Okay, so Psi1 and Psi2 I have to find out. So Psi1 I have to find out H1, S1, and H2, S2 also I can find out. So I can find out exergy change also, Psi2 minus Psi1. And exergy destroyed also you can find out, you can see this. Okay, this is it. So X1, M1 into U1 minus U0 minus T0 into S1 minus S0 plus P0 into V1 minus V0. So you can use all those values and you'll get 35 kilojoules. And exergy after the process, this is this, and delta X is X2 minus X1. And W useful is W minus W surroundings, and W surroundings is P0 into V2 minus V1, and this you will get, and 5.3 kilojoules. And so exergy recovered is W useful by the change in exergy or exergy that is spent. So that is 55.2%. So this is the way we can find out. So detailed problem you can see in the textbook. Okay, I think I will stop here. We will do some more problems in the next class, and we will do some exercise problems also, both in the NAG and also from the Cengel. And because we are going to get some problems on the availability in the minor, I thought we will cover these problems. Any doubts? And we will see this small story. It was a very cold winter night. Okay, a sparrow had spent 2 nights out with only the meager shelter of a tree. Actually, this is one of the management story. He decided that he couldn't survive a 3rd night, so he left the tree to find a better shelter. As he flew, he got colder and colder until his little wings froze solid and he fell to the ground. As he lay there, freezing, he realized that his end was near and he prayed for death to come quickly. Suddenly, in his semi-conscious state, he had a feeling of being enveloped in a warm covering. He regained consciousness to find that a friendly cow had dropped a luxurious deposit that shit all over him. And suddenly, because of that, because it is warm and all, it is comfortable. And the warmth gave him a new lease of life. And the sparrow's comfort made him feel very happy. So he started to sing. A passing pussycat heard the chirping, located the heap, carefully removed the excrement to reveal the little sparrow, and promptly ate him up. Okay, this is not a story which is nice and touching and all, but there are some things to learn from this story. Okay, it's a small story, but good things he talked about. Okay, one in common language and one in a polished language. Okay, there are three morals to this sad story. One, if someone cheats on you, they are not necessarily your enemy. So that cow, right? So, and someone gets you out of the shit, they are not necessarily your friends. And if you are in the shit and happy, keep your mouth shut. Okay, these are the lessons he told. But okay, this is for a common man. And in a better way, it is given that if someone harms you unknowingly, they are not necessarily your enemy. If someone tries to help you out, they are not necessarily your friends. Because there may be some motive behind it. We don't know. And so we should not get deceived also. Even if you are not in very good condition but are happy, keep your mouth shut. Don't cry that I don't have this and that and complain. Okay, so right, this is the message I wanted to send. Okay, thank you very much, and happy Diwali again. Anything else if you want, you can just thank you, happy Diwali. Thank you Raghuvanshi. Thank you Maharaj. Thank you Daneshwar. Thank you Raghuvanshi. Thank you Deepak. Thank you Vamsi Krishna. Thank you Harsha. Thank you for Jagdish. Thank you Manoj. Thank you Karthik. Thank you Raghuvanshi. Thank you Shivaprasad. Thank you Satish. Thank you Shahir. Thank you Shivam. Thank you Karthik.